Okay, welcome back. I sent out a message to the lab center. I haven't heard back from them yet. I was hoping to go up to the school this week. Well, not today, but if we went up there, would be Wednesday. So I'm looking to hear back from them. So guys, I need you to just kind of watch your emails, your announcements, and all of that, because if they don't get back with me today, it might be tomorrow. I really don't know if they can schedule it as quickly as Wednesday, but hopefully they can. But if we do end up going up to the school, you'll need to, I'm sure they'll have you have a mask and social distance and all that stuff. So again, I haven't heard back from them, but as soon as I hear something, I'll let you know. And if I don't hear back from them by like early tomorrow, then I don't think it'll probably be a no-go for this week. We'll see. Anyway, so we were talking about resonance, series resonance, and we did a calculation of like a practice problem on the handout, and so there's a couple more practice problems on the handout. So what I want to do today is to finish up the practice problems and finish talking about series resonance. I'm going to talk briefly about parallel resonance, and then I want to move on to a new topic called transformers. So probably what I'll do is introduce transformers to you, and then or actually we need to do a review. Part of the transformer lecture is to review magnetism. So we'll review that, and if I get, if we have enough time, I may introduce the system, transformer system to you, and then we'll see, we'll go from there. So what I need you to do is get your handout from last class on resonance, and we were working at the bottom of the page, our three practice problems. We went through the first of the three. They're not numbered, but there's three at the bottom. And I think we're on the second one. And in case you don't have your paper, I'll read it. It says the bandwidth of a series circuit is 400 hertz. The resonant frequency is 4 kilohertz. They want to know the Q. Q stands for quality factor, by the way. They want to know the Q. They give you a value for R. They give you a value. Now they want to know the value of XL at resonance, and they want you to find the value of L and C, that is the inductance and the capacitance. So if you don't have the sheet, I believe it's online, you can bring it up. But go ahead and draw the circuit first, even though you might be able to work it from the problem statement directly. It's always good to draw a picture when you're trying to solve a problem. So I'm going to draw the picture, and I'll put the values here in case you didn't get on point when I read it. So we got a series resonance circuit. They give us the bandwidth of the circuit. It tells the bandwidth is 400 hertz. Let's see. They give us the resonant frequency, 4 kilohertz. It tells us that the resistor value is 10 ohms. We want to know Q. We want to know XL. We want to know L, and we want to know C, given the information shown. So bandwidth, 400 hertz, 4 kilohertz resonant frequency. We want to know Q. We want to know XL. We want to know L and C. They give us the value of R. So this actually is not too bad. So go ahead and see what you can do with that. It's just from what I can see, is just using the formula, so that shouldn't be too bad. Anybody get Q yet?
I got 10.
Okay. Q. So Q is FR over BW. It gave us 4,000. It gave us 400. 10. So Q is 10. Okay. We got that one. Just using the formulas. Not too bad. And then we need to get XL. Of course, if you know Q, you can get XL pretty easily since they gave us R. Anybody get XL?
I got 100
Ohms. So we know that Q equals XL over R. They always do, even though at resonance Q and XC are the same, they always use the coil for Q. So we want to know XL. So XL is just Q times R. You got 10 for Q. We got 10 ohms. We get 100. So that's correct, 100. And if we know XL, then we can get L pretty easily. You know the formula, which I'm sure you guys do. So XL is 2 pi FL. We found that, they gave us that, we can get this. So L is going to be XL over 2 pi F. 100. I'm going to leave the units off. We'll end up in Henry's. 100 on 2 pi 4,000. What you get when you do that? 100 divided by 2 divided by pi divided by 4,000 is what? I guess I did find my calculator, by the way. It's been missing for like 2 weeks. And I actually had it in my book bag, must have in one of those hidden pockets. So I got 100 divide 2 divide pi divide 4,000 I get, I can't even see my numbers. About 4 millihenries. Is that what you guys got?
Yeah, like 3.98 milli.
Okay, so we'll go with that. And this problem might be too easy. Well, I mean, it's kind of like a workout with the equation, so it wasn't meant to be difficult, really. If you know your formulas, then it's simple. If you don't know the formulas, it might not be so simple. Okay, so now we want C. We know that's the same as, a resonance is the same as XL, so I can just stick that value in there. As we said, XL was 100. So for F was 4,000. XC is the same as XL, which is 100. And again, I'm leaving the units off. And we do 2 times pi times 4,000 times 100. And do my reciprocal key. I don't know if I did that right. I got about 0.4 microfarads. Did somebody get anything different? Let me make sure I did that right.
It says, yeah, 3.98 to the times 10 to the negative 7.
Is that 0.4? I got 0.4 microfarads. Let me just make sure. Hold on a second. I got 2 times pi Yeah, that's what I'm getting. I'm getting like 0.39 micro, 0.397 micro. So I'm getting about, I just rounded, right? Okay. So we're done. That was easy. That was just using the formula. So that wasn't too bad at all. So we got one more to do. And then we can get off this topic and go to something else. I like resonance. It's my favorite topic, but now I'm kind of bored with it for some reason. I don't know why. I want to move on to I want to move to transformers. I was so excited when we got to resonance, but I'm kind of burned out by resonance for some reason. Here's the last problem. A series RLC circuit has a series resonant frequency of 12 kilohertz. They give you the resistor value is 5 ohms. They say if the XL is 300 at resonance, they want to know the bandwidth and the cutoff frequency. The cutoff frequency is what we call F1 and F2. They have a lot of different names. So here they call it the cutoff frequency. I want you to draw the resonant cut showing all important. I guess that must be the resonant curve, but there's a typo there. I want you to draw the resonant curve and show all the important points. So let's draw the circuit for this problem. And we can just use this circuit right here. So I think everybody understood this one. There's nothing special about the problem we just did. All right, so we got this time, it gave us 12 kilohertz. That's my resonant frequency. They give us a resistor value of 5. And they say XL is 300. Given that, we want to find the bandwidth. Sometimes in certain books, they'll use a delta F for bandwidth. So sometimes, they'll use this. I've seen that in different books. So either one of those symbols they usually use for bandwidth. But they want us to find the bandwidth. They want us to find F1 and F2. And they want us to draw the graph for the circuit. So you go ahead and see what you can do with that one. Again, it's just using the formulas. I don't think there's anything special about it. I don't have my notes on transformers. I don't really need them. I can do it from memory. Okay, so yeah, bandwidth, cutoff frequencies, and the graph is what we want. So give me a minute to do that, and we'll do it together. Oh yeah, 3 people attending class. Okay, well, I don't think this is a big deal either. So let's think about what we got to do here. We want the bandwidth, so that means we're going to probably going to use this formula. And they gave us the resonant frequency. We can get Q from the circuit because we know that Q is XL over R. And they gave us that, so they must want us to use it, this formula. We get 60 for Q. And so we can put that in that other formula, and we can get the bandwidth. We got 12,000 hertz. We got 60. So what's that gonna be? Two zeros.
Yeah.
That's a tiny bandwidth. Now, remember what I said about audio? The bandwidth for audio for human hearing is from 21 hertz up to 21,000, or just say 0 to 21,000 to make the math easy. What are you going to do with 200 hertz of bandwidth? You can't do anything with that. The other problem was 400, and I thought that was tiny, but this was even smaller. So that's not really a practical I guess it depends on what you're doing. If you're just transmitting a tone, like a tone to control something, that probably would be all right. But you can't do much with just 200 hertz. I don't know. Anyway, it's just a practice problem. So we found the bandwidth. Now we got to get the cutoff frequencies. And I think Jacob gave us the formulas. You guys probably don't remember, but last time we were together, he gave us the formulas for F2 and F1. He said that this would be the resonant frequency plus 1/2 the bandwidth. And this would be the resonant frequency minus 1/2 the bandwidth. So if you don't remember that conversation, you can go but listen to the video. But I think we took the graph and we figured out, he said what the formulas were, but I took the graph and I kind of showed you how you probably thought about to come up with the formulas. So we can just use these, you can just write them down and use it, but from the graph, you should be able to derive the formulas for F1 and F2. And these should make sense to you. So go ahead and use those to give you the value for F1 and F2. This is going to be 12, well, what was it? What was my bandwidth? Was 200? I guess I can write it as, so my bandwidth is 0.2 kilohertz. I don't want to do it that way. I'm going to do 200. This seems tinier when you write it as a decimal like that. So this is going to be 12,000 plus 200 over 2. And this is going to be 12,000 minus 202. So for F2, we get 12,100 hertz. And for F1, we get 11,900 hertz. So now what they want us to do is to take those three values and make the graph from it. That's this last part. So they want us to take, where's my resonance? They want us to take this, that's F1, and this. And they want us to make the graph. So let's make the graph. But now you know all the important points on the graph, I guess. I'll put it right here. So right here we got 12 kilohertz. And then right here we got 12.1 kilohertz. And then over here we got 11.9 kilohertz. Then our graph's going to do like this. Probably not as symmetrical as I like it to be, but you get the point. And then what are my important points? Well, one is this. That's Imax. So Imax, we can't get Imax. They didn't give us a voltage, did they? All right, I'll just call it Imax. Did they give us a voltage? Why would they ask us for? Okay, all right. They didn't give us the voltage, but it seemed like they would have to get that point. But we know what it is. And then the other important points is, of course, this one, because these two are going to tell us where our half power points is. Or if we knew that, we can take 0.707 of that and go over there. So then we got our half power points. So we got the maximum current, we got our half power points, we got our corner frequencies, our cutoff frequencies, and that's pretty much it. Then this right here, of course, defines the bandwidth. And there's your graph. Okay. Funny when you make something to a graph, the same information is there as the numbers, but it just makes it so much more pleasant to look at. You can like see it right away. That's why it's always good to make a graph. Okay, so that's it on series resonance. Anybody have any questions or comments on series resonance? So we did ask a question. I think Jacob did some research on these half power points, and it turned out it was related to RMS. I still don't know why it's related to RMS. So
did I not explain well enough what I found?
You explained. You just said that before when I read it, it just kind of didn't explain why they use RMS though. It just kind of talked about the fact that they used RMS.
Well,
But
so what the RMS was just specifically for a sine wave.
yeah,
They had a big calculus problem, and
yeah,
what it all boiled down to was 1 over the square root of 2,
yeah. I
which is
saw
what
that.
the 0.707 comes from. So you end up with half of the power when you take RMS of the current and RMS of the voltage. So you do
Okay.
the 1 over square root of 2 times 1 over square root of 2 is exactly half. So
Okay.
with the RMS voltage and the RMS current, to get your power, it ends up being exactly half power.
I get it. Yeah, because a radical 2 gives you a 1 over square root 4, and that ends up being a 2. I think I follow what you're saying. I'll read it again. I just kind of skimmed through it. And
Yeah, I was reading. It wasn't all about electricity. Obviously, some of it was just math stuff, and some of it was
yeah.
just waveforms. But that's kind of what it all came together with.
Okay. Well, thank you. That was good stuff. So all this stuff is interesting if you think about it. I don't want to go off on a tangent. So, okay. So, any questions over series resonance? Because I want to move on to parallel. I'm just going to say a few words about it, and then we're going to start a new topic. Well, we got to review magnetism before we start a new topic. So, anybody have any questions or comments on series resonance? I think I might have lost somebody. Did somebody? Oh,
Dominic
just.
signed on, and
We
then
had four
it
people
bumped him off. I think he's coming back.
kicked him out. Okay, I'm gonna pause for a minute for him to get on. He might be having trouble logging on. Spencer, is that your daughter? You got a baby girl, baby boy?
She's good.
Baby girl. How old is she?
She's one now.
Not Jacob, you got a boy, don't you?
Yeah, he'll be
I
4
met your
this
son,
year.
I think. Oh, you got him. Okay, he's a lot bigger. My nephew's son is 4. Dominique, are you here yet? I see his image, but are you
It shows
on?
on.
Are you on, Dominic? Can you hear us? He's still signing on. Okay, what I want to do is review magnetism. I'm not going to go into all the detail that we went through in DC, but I do want to do a brief review, enough so we can talk about transformers. So transformers are a electromechanical device. I don't know if they're really proper to call electromechanical because there's nothing that moves. I have to think about that. But it's based on magnetism. Dominique? Well, he might be having trouble. I see his image, but he can't hear us. I mean, he can't respond. Maybe he's having some kind of issue. So remember when we talked about magnetism back in DC, just some basic stuff here. First of all, if I have a permanent magnet, one of the things we talked about is that all magnets have poles, the North Pole and the South Pole. You can't see it, but radiating from all magnets are a magnetic field. These lines of magnetic force, they're called flux. And so we usually draw them like this with an arrow to indicate that flux has direction. And I'll just draw a few lines right here. And the rule is that magnetic field or magnetic flux, these lines of force, they don't cross each other. They radiate from the magnet in the direction I'm showing you. And at the poles, they're really close to each other, but they never touch each other. They kind of push away from each other. And they actually extend all the way through the magnet. We talked about, when we talked about magnets back in DC, we called this flux. So right there, that was flux. You might remember that flux, the symbol for flux was this. That's the Greek letter, I don't know if it's phi or phi. I always say phi, but it might be phi. And that the unit for flux, there was a couple units. One was the Weber, and the other was the Maxwell. So we talked about Webers and Maxwells. And then what's important though is not flux by itself, but how much flux you have per unit area. So if I take a unit area, I take an area, like a square area, and I count the number of flux lines that go through it, we call that the flux density. Flux density. And that's important because it tells us the strength of the magnetic field. I mean, if you think about it, if I have a unit area like this, and I look at the number of lines of flux that go through it, like there's 3 right there. If I go to the poles, it's twice as many. So since I have twice as many lines in the same amount of area, then we will say the magnetic field is stronger at the poles than it is out here or over on the other side. So this idea of flux density is important. It's the flux over the unit area. And when we say that, we use the symbol B for flux density. I don't know what the B stands for. Of course, we use this for flux and A for area. So when we were in DC, I gave you this formula right here for flux density. And when you talk about the magnetic field, that's what you're talking about. You're talking about the flux density. Usually, you don't mean flux. You could, but usually you mean flux density. That's what's important. Well, if we look at the units of flux density, which of these we use, if we use the Weber, then we got to make the area in meters squared. The reason is, when we talked about systems of units, there was the MKS system, and there was the CGS system, and Weber was over here, and Maxwell was over here. And for this is the meter kilogram second, and this is a centimeter gram second. So if I'm over here and I want to get area, it's a meter times a meter, whereas if I'm over here in the CGS, it's a centimeter times a centimeter. So if I'm using Webers, and this is in meters, and then we said that a Weber meter squared, we gave that the unit of a Tesla. Tesla. And you guys know about Tesla, Nikola Tesla. Or if I wanted to, I could use Maxwell in that for the top unit. If I use Maxwell's there, I gotta use centimeter squared there. and then my unit would be Gauss. So these are some units for flux density. Basically, a Tesla is a big unit of magnetic flux density, and a Gauss is smaller units. Just like a meter is a big unit for measurement, a centimeter is a smaller unit. This is a big unit, that's a smaller unit. So we talked about that. And this is enough for you to worry about. I just want to bring up some of the vocabulary that we talked about. We talked about magnetic fields. So that was the main part when we talked about permanent magnets. Then we talked about electromagnetism. And if you remember, electromagnetism is the magnetism created by a current carrying conductor. So what is that about? Well, if you have a piece of wire, and there's current flowing through the wire, then there's going to be a magnetic field surrounding the wire that's proportional to the current creating the magnetic field. All current flow creates magnetism. So if you have a wire, it's a small piece of wire. Even when you plug your cell phone into the wall, there's a magnetic field around the wire going from the wall to your cell phone if you charge your cell phone. Now, usually when we have the wire, spread out like that, the magnetic field is really weak. But if you wanted to, you can take that wire and coil it. If you coil it, you take all that magnetic flux and you push it into a smaller area, and it makes it stronger. And it's even stronger if you put like a piece of metal in between called a core. We'll talk about that. So the flux density is caused by current, and the relationship is the flux density is directly related to the current. So the more current I have, the more magnetic field I have. The less current I have, the less magnetic field I have. So we talked about that. And then at some point when we talked about magnetism, I had you watch a video, and I'm not going to have you watch the video again because you already watched it at the beginning of this semester. We looked at Faraday's law. So we got to revisit Faraday's law again. So in the video, if you remember, the guy had a coil of wire. He had 3 coils. He had a coil with 1 turn, a coil with 10 turns, and a coil with 100 turns. He had a meter. It was a special kind of ammeter. The zero of the meter was like right in the middle. That's what 0 was. And the needle sat kind of right in the middle. And what he did, he took the single loop coil and the magnet, he moved it in and out. He moved the magnet across the coil, so the flux cut across the coil. And what you saw was when he went one way, the magnetic needle deflected one way, and when he pulled it back, it deflected the other way. And I used that to talk about the nature of alternating current, alternating voltage at the beginning of this semester. You looked at that video. Then he went to 10 loops and then 100 loops, and the idea there was the more loops, the more voltage is induced. So you remember that Faraday says that if I have a conductor or a coil, if I have a magnetic field, and I have movement or motion between the field and the coil, then you can induce a voltage. If that voltage is connected to a closed circuit, that voltage can cause a current to flow. But the current is going to be alternating in nature. And we went through the whole spiel of that at the beginning of this semester to see why it was sinusoidal as opposed to some other shape. So we went through all that. But this is big, this idea of Faraday's law. Well, in AC, we're allowed to do something else, though. Here's what we said about AC. If we wanted to, Faraday says, I don't care if you move the coil, I don't care if you move the magnet, you just got to move something. So in the video, the guy had the coil, and he took the magnet, and he moved it in and out like that. If he wanted to, he could have held the coil, the magnet stationary, and moved the coil across like that. But there's another option we could do. What if I did this? What if instead of moving the coil or the magnet, I could take my voltage source hook it up like that. And then current is going to flow. And that current is going to create a magnetic field like that around the coil. North pole, south pole, right? So if I wanted to, I can take another coil. What if I took another coil and I move that coil in and out of that magnetic field? If I did that, then I got everything Faraday says I need to induce a voltage in this second coil. And there's nothing hooked up. If I had a light bulb over here, even though these two circuits are completely isolated one from the other, if I move this back and forth and I get Faraday going on, that light bulb should blink off and on. I'm actually transmitting or transferring energy from this voltage source to the coil, through the magnetic field to the other coil, which will light up the light bulb, which is kind of neat if you think about it. But I got to have this motion back and forth. But what if we did this? What if, instead of using the DC source, what if I took that out and I replaced that with an AC source? What will happen then? Well, if I did that, I no longer have to move this coil. I can just leave it alone. I can hold it stationary. Because see, here's what's going to happen. Current is going to flow, but the current that flows looks like this. That's the current over time. Well, if current is flowing like that, it's going to produce a magnetic field that looks exactly like the current sine wave. So if I make a graph of the magnetic field produced by this current, that magnetic field, this is B now over time. That magnetic flux is doing this. What does the sine wave of flux mean? What does that mean? Well, here's what it means. It means when I don't have any current, I don't have any flux, no magnetic field. As the current builds up, that magnetic field is building up. When I say that, it's doing this. It's building out like that. At 90 degrees, I got max current. I got max magnetic field. And the magnetic polarity might be like this. This might be north, and this might be south. From 90 to 180, my current is basically going to zero. So my magnetic field is going to decrease. At zero, I don't have any magnetic field. But then something special happens at 180, from 180 to 270. My current is increasing again in the opposite direction, which is going to have the effect of putting the north pole down here and the south pole down here. But more importantly, the flux lines are now moving out across the second coil again. So if you can see this, let's say you can put on some sunglasses, you can actually see the field, the magnetic field. You will see the north pole and south pole constantly flipping. One way the north will be on the top, and the other way the north will be on the bottom. But more importantly, you will see the flux doing this, coming out, cutting across that second coil, and then collapsing again. So it's actually doing this, like an accordion. So I'm getting movement, but I'm not moving the coil. I'm not moving the magnet. I'm not moving anything. The only thing I'm moving is I'm moving the magnetic field by way of varying the current. So I got everything Faraday says I need to induce a voltage over here. And in fact, what you would see, that light bulb would light up. And that's kind of cool. But it gets even cooler than that. Consider this. What if I told you I had 100 turns of wire over here? No, let's say 1,000. On this side over here, I got 1,000 turns of wire. 1,000. So I got 1,000 turns over here. And over here, I have 1,000 turns. Well, as that flux line radiates out across that second coil, it cuts across the 1,000 turns. Let's make this voltage source 100 volts. No, let's make it 25 volts. So I got 25 volts AC. If I have 1,000 turns over here and 1,000 turns over there, guess what? If I measure my voltage over here, I get exactly 25 volts over here in that other coil. But let's let's say instead of 1,000 on this side, I had 2,000 on this side. Guess what happens now? The flux over here, let me make this coil bigger so you can kind of in your mind's eye see this. If I double the amount of turns, so I'm gonna make this bigger. Let me draw it another way. I want to emphasize what I'm doing. So let me make it a little bit neater. So I have this. We got 1,000 turns over here, but on the other side, I got twice as many. So I'm gonna draw twice as many. I got 2,000 over here. When that flux comes across from here, it cuts across all those loops, and I still got Faraday's law. But what's going to happen is, if I have double the amount of coils, if this is 25 volts, over here I'm going to get 50 volts. And if I did it the other way, let's say I went from, instead of having twice as many, I had half as many. Say I had 1,000 over here, and I had 500 over here, then I get 12.5 volts. And you're probably thinking to yourself, well, just hold on for a second, Singleton. Let's go back to the 50 volts. I'm not buying that. You're telling me I can put $25 in the bank and get $50 out? Nature does not ever give us something for nothing. We got to give up something. I mean, this seems like an impossible situation. And if you think about it like that, it kind of is, but the voltage is not what's important. Here's what's important. What's important is the energy. Here's the way to think about this. Well, actually, do I want to explain that now? Well, I guess I could. So, the way this works, let's look at this as a black box. Even though we know there's coils in there, let's just say we can't see inside the box. We got this box, and I got these two leads coming in here. I got these two leads coming out. The only thing that has to be true, according to physics, is that the energy I put in got to equal the energy I get out. So En is going to equal E out. Now, engineers don't usually talk about energy. Engineers usually talk about energy per unit time. If you remember, energy per unit time, well, we call that power. It's kind of the same thing, but so it's better to talk about P in and P out. In physics, I like energy because I'm a physicist, but in engineering, they like to talk about P in, P out, and that's okay because all I got to do is divide both those E's by T. I get the same thing. Not a big deal. So what has to happen is just like energy in has got to equal energy out. Well, what has to happen here is the power in has got to equal the power out in any combination. Any combination. So the fact that I put in 25 volts and get out 50, that comes at the expense of something else, and the something else that comes at the expense of is the current. So here's what I'm saying. Let's say that this system right here is 12 watts. This is a 12 watt. These two coils I put in 12 watts, right? It's a 12 watt system. Maybe I put this 12 watts in like this. Maybe over here, I put in 3 amps of current, and I have 4 volts of AC voltage. And so I know that P in is going to equal V in times I in. So that's going to equal 4 volts times 3 amps. Well, that's going to give me my 12 watts I'm talking about. That's my 12 watts. But if I use more coils, I make that voltage bigger. Let's say on this side I get out 12 volts over here. I get out 12 volts. Well, the only way that can happen, only way I can get out 12 volts over here and not violate the conservation of energy principle, which is this. The only way I can get that out and maintain this is that my current has to drop down from 3 amps to 1 amp. And then I still have 12 watts coming out of this device. So the thing here is, you might think, well, dang, we're getting put in 25 volts and getting out 50. Boy, I wish my bank account worked like that. But you can't get something for nothing. And the thing that has to stay the same is the energy, i.e. the power. And so if this is a 12-watt system, you put in 12 watts, you get out 12 watts, but nature allows us to do it in any combination of voltage and current we want. So I want to put in the voltage at 4 volts, 3 amps. I can get it out at a higher voltage, 12 volts, 1 amp. That's called stepping the voltage up. Or if I took the power source and put it over here, I got more coils over here. I got half the coils over here. Then what I'm going to get is half the voltage. I'll get half the voltage on that side. And again, if I get half the voltage, I cut the voltage in half, the current's going to go up. So nature allows us to play with this combination of V times I, but what has to stay the same is power, really energy, but the power going in and the power going out have to be the same. So it's not magic. It comes at the expense. Raising voltage up drops current and vice versa, but the power is what has to stay the same. So there's a name for this system. When you take 2 coils and you let one coil link the second one with the magnetic field, there's a name for that. It's called a transformer. So let me draw the picture a little bit better. A transformer. So write that down. A transformer. Transformers. And sometimes they'll abbreviate this like this. So and then sometimes electrical engineers, they'll write it like that. X-former, transformer. It's kind of like a little shorthand thing. I heard a corny joke on the radio yesterday. It said, "Tell the people that invented zero, thanks for nothing." No laughter, no nothing.
Sorry, my mic was
I
muted.
actually kind of like that. That's actually funny.
Well, okay, well, you should turn your mic on and laugh, and then muted it back. I wish I had thought of that, but I can't claim credit for it. But I was in the car, so they said that. I just started laughing in the car by myself, which made me look retarded, but I am retarded, so I can't say that. That's not politically correct. It's, what is it, Dominic? Mentally challenged? I think I'm mentally challenged, so.
Very much so. I'm not.
You don't have to agree.
I'm not agreeing. I'm just saying.
That's cold. You guys, you hear what he called me? He said very much so. Sales is very much so mentally challenged. Okay, and I got it on video too, so I'm recording it. All right, so here's a symbol for the transformer. All it is 2 coils. Now, there's no difference between the left side and the right side. I can put the power source over here, or I can put the power source over here. Whatever side you connect the power source to is called the primary coil. So I'm going to put it on the left. And this is called the primary coil. But they usually don't write the word coil. They just drop it. It's just primary. And on the other side is the load. That's the thing you want the transformer to run. And usually it could be a light bulb, doorbells use these. The thing that you plug into the wall when you charge your cell phone, that's one of these. So we just use whatever it is. We just put a resistor there to represent the light bulb, cell phone, whatever. A resistor can represent anything. We'll just call this the load. And this is called the secondary coil. But again, they usually drop the word coil, and then it's called the secondary. So they use the term.
I have a question.
primary and secondary. Go ahead. You can just interrupt me.
That's okay. Is this also what would be referred to as primary windings and secondary windings? Okay.
Yes, exactly the same. So these are the windings, the coil windings, and I mean, I'm giving you a very simplified explanation of this, but those coils can be wound different ways, and there's different. We'll talk about some of that, but we won't go into the details of this because this is kind of like the beginning course of it. But again, you can take a whole course just in transformers. Transformer theory can get really, really deep. I don't know if they still do it, but I don't even know if this guy is still teaching because he was my teacher. I graduated college in '96. And I took a course at UC, 4 years ago? And the professor that taught me when I was in school back in '96 is still teaching. He was up until the year before last. I know he was still teaching. He was like 300 years old, Professor Everly. But he taught the machine and power course. In that course, you actually build a transformer from scratch. And you have to learn a lot. Now, I don't know if he's still around or if he still might have retired by now, but I can guarantee you, you will never find teaching like that again. So he's old school. So he actually had his students learn by building this thing from scratch. So I didn't do that, but that's what he does in his course. And that would be the primary winding or coil. And you would learn that kind of terminology if you have to wind your own transformer, which you can do. Once you understand the physics behind this, you really could build your own transformer if you wanted to. So yeah, that is the primary winding. Now, here's how this works. You kind of can see how it works from what I said before if you understand Faraday's law. It's not really magic because we have energy here. The energy is moved from the voltage source. The energy is moved from the voltage source to this primary coil, right? And from the power source from here, this coil converts it to a magnetic field. So now the energy is moving across this gap here in the magnetic field. The same energy that was over here as electrical energy is now between this gap right here as magnetic energy. And then when it moves out across this coil, Faraday happens. Faraday's law changes that back into a voltage, which causes current to move on the other side. And now I've changed it back to electrical energy, which now goes to my load, whatever that is, a light bulb, cell phone, whatever. It's going to change to a different form of energy over here. So all I'm doing is basically changing form of energy. And then this gap right here is magnetic. So it almost looks like magic because these two circuits are completely isolated from each other, which makes this nice. Sometimes you need electrical isolation in certain applications. You would use this device. But you actually have current flowing, not current, energy flowing across this gap, and it seems like magic, but remember what exists there that you can't see is the magnetic field. So we as technical people, we understand that it's not magic. There's actually energy flowing through the magnetic field. And remember from DC what I said about fields. Fields can carry forces, and fields can carry energy. And so far, we only know about three kinds of fields: the electric field, the magnetic field, and the gravitational field. And all those fields carry energy. So it shouldn't be anything so shocking about this, the fact that that magnetic field is carrying energy. If an electric field can carry energy, you call a radio wave, then the magnetic field can carry energy and produce Faraday effects on the other coil. So now, we do have a problem though. The problem is that in order to use this, since the energy is actually carried by the flux that cuts across the coil, you see the problem I'm having here? I'm drawing something that's three-dimensional on the two-dimensional surface, so you keep that in mind. But let me draw the flux, what's happening here. As the current flows and varies in this wire right here, it causes electric flux or magnetic flux to move out this way and cut across, and that's Faraday. If I see the flux cut across the coil, you see Faraday there. I got movement, I got magnetic field. So I'm going to induce a voltage over here. But the problem is some of the magnetic field is moving back this way too. And some of the magnetic field is moving towards you. And some of the magnetic field is moving into the board. It's three-dimensional. So the problem is, in a perfect world, what I want is whatever energy I'm taking out of here and putting over here, I want all of that energy or most of that energy to come over to this secondary coil. But that's not happening because the magnetic field is radiating in all directions. And only the flux lines that cut across this secondary coil contribute to the energy in the secondary coil. And that ain't good enough. We got to make this thing more efficient. How are we going to do that? Well, let's think about it. Remember in DC, let me use my purple marker. Remember in DC, if you did this, let's say I take a battery and I hook it up to a light bulb. And of course, the light bulb will light up. But now, while that light bulb is lit up, I take a metal rod. Let's say this wire is bare wire. I take a metal rod and just lay it across the circuit like that. If I do that, what's going to happen? That light bulb is going to go out. Why will it go out? Well, the reason it's going to go out is because current takes the path of least opposition, least resistance. The current's going to come out of here. Instead of going through the light bulb, it's going to go through here and back to the battery. That's called an electrical short. You said we got a short circuit, so the light bulb won't light up. Current takes the path of least resistance. It turns out that magnetic flux does exactly the same thing. Magnetic flux takes the path of, now get this, when they talk about current flowing, they call the opposition to current flow resistance. They call the opposition to flux flow reluctance. The R thing kind of gets me. But resistance and reluctance. Resistance is opposition to current flow. Reluctance is opposition to the flow of magnetic flux. So flux takes the path of least, not resistance, flux takes the path of least reluctance. So I can have for all practical purposes, I can have an electrical short, but I can also have a magnetic short. You can have a magnetic short. What would that look like? Well, let's think about it. What would that look like? Here's what it would look like. If I take a magnetic field from a bar magnet, here's my bar magnet, and we know the flux will do this, right? Just kind of going through the air. But now let's say I get a solid metal pipe, something that can be magnetized like iron. Iron can be magnetized. So I got an iron pipe and I did this. I just came over here close to this. If I did that with that pipe, let me show you what's going to happen. What will happen is the flux is going to do this. The flux, instead of going, this is the shortest path, direct path, but it's going to go all the way over here and come back like that. Like that. You might say, well, why would it come all the way over here? Why wouldn't it just take the shortest path? Well, because flux takes the path of least reluctance. And to go from this point to that point, it's easier to go through the metal object, the iron, than it is to go through air. Because air has a higher, not resistance, has a higher reluctance. So flux takes the path of least opposition, least reluctance. So this is what we call a magnetic short. A magnetic short. Well, somebody looked at that, and they looked at this problem over here of the flux lines going back that way towards you into the board, three-dimensional, and they said, I wonder if it's a way, what if I did this? What if I took a hunk of metal, I need a hunk of metal, there's a hunk of metal over there. What if I took a hunk of metal like this? It's a book, but imagine it's a hunk of metal. What if I took a hunk of metal like this? A square piece, rectangular piece of metal, and I maybe took a laser and cut the middle off and I knocked it out like that. So I got a hole in the middle. So then I have something like this. I got the metal remove the center of it. And then I take my primary winding and I wind over here. And I take my secondary winding and I wind over here. So here is my voltage source. Here's my load. Now how would that work? What will happen? Well, what will happen is we still have that same build up and collapsing of flux. But since flux takes the path of least, not resistance, flux takes the path of least reluctance, it's a magnetic short. So all the flux that would have been radiating out, radiating towards you, moving into the board, all that flux now flows through here because that's a magnetic short. So practically, not all, but ideally, 100% of the flux produced over here would travel through this piece of metal. By the way, this metal is called a core, and it's usually made of iron. They call it an iron core, just core for short. But what we do now is force the flux to travel in this magnetic short, the iron core, and so almost all the flux now links the second coil, which means almost all the energy produced by that voltage source is transferred through the flux, not through the metal core, but through the flux in the core. We still have Faraday effects over here, and all that energy now is, I think, is available to go to the low resistor or whatever we have over here we're running. But in solving one problem, we kind of create another. Let me show you what that is. We solved the problem. We directed the flux, all the flux, which has the energy. We want to direct that energy. We direct all the flux to the secondary coil. Doing that, the problem we create is this. Inside the core is a conductor. Usually it's iron. I have a magnetic field inside the core. And since I'm producing or I'm driving that magnetic field with a sine wave, the magnetic field is varying, so I have motion. Well, you might recognize this as the three ingredients Faraday says we need to induce a voltage. So what's going to happen is there's actually a voltage induced inside the core. But the core is one continuous piece of metal. So I have a closed circuit. If I have a voltage in the closed circuit, guess what I'm going to get inside the core? I'm going to get current flowing. So not only do I have magnetic flux in the core, I also have current flowing in the core. So there's a current flowing in the core. So I'm going to call it an I core. Well, remember the resistance of wire equals rho L over A. And even though you think that's just for the resistance of wire, this is for the resistance of any kind of metal conductor. Wire just happens to be round, but this is a conductor. So just like there's wire resistance, there's a core resistance. Even though it's probably pretty low, there's a core resistance. So if I have a core current, if I have I core flowing through the resistance of the core, R core, if I square, then what I get, I squared R, I get the power in the core. The problem is we don't want the power in the core. We want the power over here to the load. So any power that's created that's not going to where I wanted to go, we call that a loss. So that's a power loss. So in fixing the problem of the varying rate of magnetic field, we create a core loss. It's just a trade-off we have to live with. You can't get rid of it. So in a perfect world, for a transformer, P into the transformer would equal P out. That's a transformer that's 100% efficient. But in the real world, you can see from what I talked about that P in to the transformer is really going to equal P out plus P core loss. Sometimes that number can be kind of high. If you plug a transformer in, and you guys probably use transformers and don't even realize it's a transformer. Like I said before, not all cell phone chargers, but a lot of cell phone chargers, that little thing you plug into the wall with the little blades on it, that's a tiny transformer. And if you put your hand on it, you'll feel heat. Why do you feel heat? Well, remember, a coil is just an inductor, so inductors can't dissipate power. You know, from we talked about AC power, inductors can't dissipate power. They take energy and they return to the system. But remember that inductors made of wire, and that wire, by that equation I just erased, has resistance. And so the heat that you feel when you put on your cell phone charger is the coil resistance. It's like a core loss. You actually feel that core loss as heat. Now, what we do in this class, we assume that we have a transformer that's 100% efficient, which makes our calculations a lot easier. We assume that this is the case. We're going to deal with transformers that are 100% efficient. So, when I have a transformer that has an iron core like that, let me show you the symbol. There's 3 symbols that you'll see with transformers. One symbol is like this. Let's call it an air core. There is no metal core there. This is usually used at really, really high frequencies, like radio frequencies. And then there's the one like this. They have these dotted lines. I'm not gonna, don't get me lying. I think this is called ferrite. Ferrite. But don't write that down. I might be wrong. I never worked with these. The one we're interested in is this one. 2 solid lines. That's iron core. That's the one we're going to talk about in this class. And these are usually used for power. These are called power transformers. So most of the time, this is probably like 99 times out of 100, you deal with a transformer, it's this kind. Not that one or that one. It's mainly this one. Unless you're in some kind of special application, it'll always be this one. So let me put my schematic back up there again. And I want to give you some more names. So now we got the correct symbol for the transformer. I'm going to draw it neater now. So here we go. We got our and there's our source voltage. There's our load. This is the primary coil, and this is the secondary coil. Or, Jacob, primary winding, secondary winding, same thing. Some important quantities. One important quantity is N pri. Now, I'm not going to write it on the board, but I want you to write it in your notes. N pri is the number of turns on the primary coil. N pri, the number of turns on the primary coil. And then there's N sec. N sec, or N secondary, is the number of turns on the secondary coil. The number of turns on the secondary coil. And here, we got V pri, which is the voltage from that coil to that part of the coil to that part of the coil. And over here, we got V sec. which is the voltage in parallel with the secondary coil. So the number of turns on the primary, the voltage across the primary, number of turns on the secondary, the voltage across the secondary. Those are important. And then one more, we got the current in this coil. We call that I pri. We got the current in this coil. We call that I sec. So there's your full schematic for a transformer. Now there's just one more thing I want to show you. There's something called phase dots. Let me write that down. Phase dots. Phase dots. Sometimes when you look at a schematic of a transformer, you'll see these dots like this. You might have 2 dots on the top or 2 dots on the bottom. It doesn't really matter where they're drawn. Let me tell you what that means. If this is my input wave, my primary voltage, and my secondary voltage is like this. But it might be bigger or smaller, depending on if I have more or less coils over here. So these phase dots, what they mean is that the primary voltage and the secondary voltage are in phase with each other. Or I might have something like this, where I have one on the top and the second one might be on the bottom. And if you see that, that means that there's a 180-degree phase shift from the input to the output. So if the input is like that, if you see the dots like this, then the output would be like this. Now, most of the time, the phase doesn't matter if you're just dealing with single phase electricity, which is all we've been talking about so far. But I'm saying this and laughing because we're supposed to go over 3-phase power, but I don't see how we're going to do it. I just don't think. Usually I have trouble doing it in 15 weeks. I don't know how we'll do it in 10. But if you have more than one phase, then this could be an issue. Now, all the phase is a coil. So you already know that how a generator works, right? You know that a generator is basically this with a coil in there that produces a sine wave when I turn it. Well, it turns out that you can have as many coils in there as you want. You can have 2 coils in there, maybe one like that and one like that. Then you have 2 sine waves produced. They call that 2-phase. Or you might have 3 coils in there that you rotate. They call that 3-phase. You can have as many coils as you want. It turns out that if you get over 3, then it becomes more impractical because they usually stop at 3. So 3-phase is the type of power we really transmit. When it goes to your house, they switch it from 3-phase to 2-phase, and they split that to single phase. Like, you don't have to know this. You don't worry about it. If I have time at the end of the semester, we'll go into multi-phase networks. But probably I've been teaching at Cincinnati State since 2013. I probably only got the 3-phase maybe 3 times. Probably no more than 3 times. So, and only once did I think I was able to go into that. When I took this stuff at UC, we had a whole class. We did DC, we did AC, and then we had a whole class in 3-phase power. It wasn't just a week stacked on to the end of the semester. But they don't, they don't go into that kind of detail anymore. They just kind of, it's different nowadays. I don't know why. I guess the internet has made things more compact. And unless you got to know, you can just look it up, I guess. I don't know. So phase dots are important. Now, I could have stopped here, but I think what I want to do, let's go into a little bit of the analytical part, the math. We won't use any of the math, but let's just come up with a few equations, and then next time we get together, we can do some calculations. So let me give you some important mathematical quantities for this. Oh, before I go into that, so here's something else you guys might want to look up. Remember I told you the core? We take a piece of metal and we knock the middle of it out. Now, by the way I drew it, you can have transformer wound a lot of different kind of ways. Like one way they do it, they'll take the core and they'll cut it like a space here and a space here, and you can wind it here and wind it there, or wind it here and put the secondary over it. There's a lot of different ways they're wound. I'm not an expert at that, so don't ask me what happens, but this is just kind of the basic theory I'm trying to give you. But what I was going to say is that if you look at a transformer closely, you'll see that instead of having like one thick piece of metal, what they do is they slice it up and make like a sandwich. It's not a solid piece, it's plates of metal together. Well, remember when I told you that we have the current? Let me go back to that. I don't know if I want to say a little bit more about that core. So remember I said you had the core. You got the core. You got your coils wrapped around it. You got magnetic flux flowing, but also what you have is current flowing in there. I call it I core. And that's what produces heat. That's what produces the core loss. Well, that current in the core is called an eddy current. An eddy current. I think it's spelled eddy, or it might be with a Y. Eddy current. An eddy current. And instead of having one thick piece, they slice it and make like a stack of metal plates to make one big core. And some kind of way that reduces the core loss. I don't know how it works. I can't figure it out. And again, that's something, Jacob, I haven't looked up. Why is it that having separate sheets that stack together gives you less core loss than a solid piece? I don't know. Sometimes students will ask that. I don't know the answer to that, but that'd be something good to look up. People that design transformer, they know about all that. I mean, that's nothing to them. But like me, sometimes I think about it, it's like, And I'm not really I'll look stuff up. I kind of like figuring stuff out myself and then looking it up to see if I'm right. But that's probably the physics in me. I don't know. So I don't know. That's something I don't think of. All this stuff I'm saying I need to think about and look up, I probably won't do till I retire. And I'm not due to retire for a long time. I'm not that old. So it'll be a while before I look this up. But that's something interesting to know. Anyway. So let me give you some quantities to write down. And I'm starting to run out of gas. So eventually, I don't know how far we'll get. But let me give you some things to write down. So it turns out that the number turns on the primary and the number turns on the secondary. While those are important quantities, they're not the most important quantity. What's important is the ratio of the two. So if I take the ratio of n sec to the ratio of n prime, if I do that, and I get this other symbol, a lowercase n, we call that the turns ratio. That's important. That's very important. The turns ratio. So this is called the turns ratio. The turns ratio. The ratio of n sec to n prime. What would you say to me if I tell you that the turns ratio is greater than 1? What would that mean? What does that mean? The turns ratio is greater than 1. What would that mean? Look at this equation right here.
There should be more turns on the secondary then, right?
Yeah. Everybody see that? If the turns ratio is greater than 1, that means there's more turns on the secondary than the primary. If there's more turns on the secondary, I already showed you what will happen. All that flux is going to link those more turns, and the voltage is going to be higher. So if I have more turns on the secondary than the primary, my voltage on the secondary is going to be higher than the voltage on the primary. We say we step the voltage up. So if I know this is the case, I call that kind of transformer a step-up transformer. Step up. Step-up transformer. If I have the other situation where the turns ratio is less than 1, that means I have less turns on the secondary than I do on the primary. And you know what that's going to do? It's going to make my voltage go down. So if I have, this is a step up, and this will be a step down. Now remember, when I step my voltage up, my current drops. If I step my voltage down, my current comes back up. So it's out the trade-off. Now the third situation I can have is this. If n equals 1, what does that mean? Well, clearly it means that I have the same number of turns on the primary and the secondary. I'm not stepping the voltage up, I'm not stepping the voltage down. So what am I doing? Well, here's what you're doing. Now you're using it as what we call an isolation transformer. If you're interested in getting a higher voltage, you need a step-up transformer. If you're interested in getting more current and a lower voltage, you need a step-down transformer. But sometimes you want electrical isolation. You want one circuit to be completely physically isolated from another circuit, then you use an isolation transformer. So if you have a situation where the turns ratio was equal to 1, this is for electrical isolation. And there's reasons why you would want to do that you can look up yourself. So one of the things I expect you to know on the quiz, which I know we haven't had a lot of, you got to know this. Turns ratio greater than 1, step up. Turns ratio less than 1, it's a step down. Turns ratio equal to 1, it's an isolation transformer. Just by looking at that in the picture, you should be able to figure that out. Now remember the diagram when we first started the class? I gave you a picture, and it had a generator station, had a dam of water, and water fell over the dam, and it turned the turbines, and had the turbines go out to a step-up transformer, and they step it up to a really high voltage. The whole reason, that's when I had the discussion, why do we need DC and AC? We need AC because we can transmit power more efficiently with AC. And I told you it was a device called a transformer, and that we would talk about it. Well, now we're talking about it. If you go back and look at that diagram, you'll see that there's step-up transformers which step the voltage up from the generator to a really high voltage. Why do you want to do that? Because if they knew if you step the voltage up, the current will drop. And so the wire loss, P wire loss, is equal to I squared R sub W, where R sub W is the resistance of the wire. If I step the voltage up, then this current is going to drop, which means that power loss will drop. So by using the transformer, some kind of way, Nikola Tesla figured that stuff out. I don't know how he did it. He figured it out. And he knew that if we use AC, then because transformers can step up voltage and transmit or distribute power in the form of high voltage, low current, then we have less power loss in the AC system compared to a DC system. No reason why I couldn't have a DC power system. Duke Energy could be DC, but then they lose a lot of efficiency. All right, so this is one important equation right here, the turns ratio. Now, okay, I'm gonna go for a couple more minutes and then I'm getting tired. So I'm gonna put something on the board, and I hope you can just kind of see from your gut what I'm talking about. So because of the fact that it takes a magnetic flux linking a coil to produce or induce a voltage, then you should be able to see that the number of turns in the coil is related to the voltage produced across the coil. The way Faraday's law works, that magnetic flux linking that second coil, if I have the same number of turns on both coils, I get the same voltage. If I have twice as many coils on the secondary as I do the primary, I get twice as much voltage. If I have half the amount on the secondary as I do the primary. I get half the voltage. So you should be able to see that there's a direct relationship between the number of turns on the coil and the voltage induced across that coil. And because of that, I can take this, I can take the ratio of N sec to N pri, and that's going to equal the ratio. Now that's kind of cool. Just from the physics of it, and looking at the picture, the ratio of N secondary to N primary is equal to the ratio of V secondary to V primary. And that's kind of cool because here's why it's cool. What if you want to know the turns ratio? What you gonna do? You gonna go here and count the coil? You're gonna count 1,000 turns of wire on both of these? You ain't gonna do that. See, if this is true, then instead of counting turns, I can just take my meter, my meter. I can measure V pri with my meter. I can measure V sec with my meter. I got that number and that number, divide them, and I got, because this right here is that. This is actually the turns ratio. So I can get the turns ratio not by counting coils, but just by measuring the secondary voltage, primary voltage, divide it, I got it. So that's kind of nice, that relationship. But here's what's nicer. It's like I got a pretty picture again. I don't want to erase it because it just, I don't know. I come back and look at that. It looks so technical. I just don't want to erase it. But I got to. Let me erase this. But here's something that's cool. If this is equal to this, and this is equal to this, that means this is equal to that. So that means that my turns ratio is equal to V sec over V pri. And if we solve this for V sec, we get a very famous equation. V sec is equal to N times V pri. And this, my friends, is called the transformer equation. Write this down. There's one. Here's another that's important. And these two are the same, just in different forms, but this is a transformer equation. So you use this and you use that. And then there's one more. The other thing we know about this, to give us one more equation, and then this will be a good place to stop. So I'm going to give you the one more equation, and then when we come back, we can actually do something with the equations on Wednesday. That's provided we don't go up to the school. Dominique, you missed that part. I sent out a message to see if we can go up to the school on Wednesday. Now, they may have texted me back. Emailed me back. I haven't looked. I'm going to go back after this. I'm hoping he did, because if we do, this will be on Wednesday from 1 o'clock until like 3 o'clock is what I'm hoping we can do. If they don't text me back, we won't be able to do it. So I don't know what we'll do if they don't, because we need to do some hands-on stuff. But we'll see. I'll let you know later today or tomorrow. Now, let me do one more thing, and then we'll call it a day. Okay, I just put it right here. So one of the things we're going to do in the class is we're going to assume that our transformers are 100% efficient, which is what they usually do on this level. Now, if you go to get your, I'm trying to think when I got my bachelor's, probably your master's, they won't make that. If you get your master's in engineering, you'll probably, and you deal with transformers or power systems, they won't make that assumption, but it just makes the math easier. So we're going to assume that the P pri is equal to P sec, and that only happens when my transformers are 100% efficient. So for all calculations, we're going to make that assumption because it makes the math easier. Since we're making that assumption, then here's what I can write. I can write, well, okay, how do I calculate from this picture? How do I calculate P pri? Well, that's easy. Watt's law says that power is just voltage times current. So P pri is just V pri times I pri. And using the same logic, P sec is just V sec times I sec. And I'm stating that they're equal. Well, let's do some massaging of this equation a little bit. And I want to get all the currents on one side and all the voltages on the other side. So I'm going to divide the left side how do I want to do it? I'm going to divide, I guess I'll divide this side by V sec. And I'll divide this side by V sec. And then this will get rid of this. So if I do that, that'll get rid of that, right? I got V sec over V sec, so I can get rid of that. And then I'm going to divide this side by I prime and this side by I prime. So I'm going to divide this side by I prime. And I'm going to divide this side by I prime. If I do that, I got I prime over I prime. They cancel out. And so what I get is I get these two ratios. The math tells me that whatever they are, they're equal to each other. What is this right here? What is that? What is V prime or V sec?
Like the inverse of the turns ratio?
Yeah, everybody see that? If the turns ratio is V sec over V prime, if I flip it over, that means that V prime over V sec is equal to 1 over N. That's the inverse. So I can replace this right here, not with N, but with the reciprocal N. This is like 1 over N. 1 over N. So then if I solve this for I sec, look at what I get. If I solve it for I sec, what I get is I sec. See, usually we always want things in terms of the secondary. So I usually want to, because we usually know the primary, I'm plugging that into a power source. For us, most of the time it's going to be 120 volts. That's what we get in the wall outlet. So most of the time you know the primary, we want to know the secondary. So usually we write this in terms of V sec, we're going to write this in terms of I sec. So if I multiply both of this side by I prime for this equation, I get, from that equation, I get I sec is 1 over N times I prime. And it has to be that way if you think about it. If you think about what I said earlier, if I have a transformer, if I increase the voltage, the current has to go down. So, and here's the voltage. If I increase the voltage, I'm increasing the voltage because I'm multiplying by this factor of N. If I increase the voltage, what am I doing to the current? I'm dividing by N. So the current's going to have to drop as fast as the voltage is rising. I hope you can see that from the math. But the math says it all. It's the language. So when we solve transformer problems, these are the 3 equations we're going to use. These are our working equations for transformers. That's really kind of it, guys. Now, transformers are really easy. Matter of fact, I think if we do go up to the school, that's one of the labs I want to do, because you can just see how a transformer works. It's simple, and I like labs that are simple and to the point. You can really take some crystal clear knowledge away, and you can do that with this. So if we go up to the thing, we need to do some stuff with the oscilloscope, but hopefully we can do some stuff with the transformer. Really, what I like to do is, for the rest of the time we have together, I really would like to meet at the school. I'm going to see if I can work that out with the dean. That would just be so much better to meet there for a couple of hours. And then, you guys can leave early if we need to or whatever. But I want to get some hands-on stuff and some face-to-face time. But I don't know if they're going to let me do it or not. The lab tech center seems to think they will, because they let the automotive people come up there. The nursing students have to go because they got to do their clinicals. You can't do that by remote. So some of the stuff that we do, we can't do by remote. So Anyway, let me not get on the tangent. You guys, anybody have any questions over transformers? We went through a lot of theory from the first principles you learned from DC and AC. You should understand this. Any questions or comments?
I have a question. So obviously the ratio of the turns is important. Are we going to be doing any math where we'll actually need to figure out the number of turns?
No. You could. I mean, you could, but usually in engineering, that would be a good physics problem. But usually in engineering, they're only worried about how something works, not why it works. So I don't unless you're designing transformers, I don't think that would be. You don't need to know that. But I mean, there's no reason why we could solve that if we wanted to. I mean that would be a good problem to do. Once we get into this, could we figure out how many turns are on a now? Right now, I'm kind of scratching my head because I know you can get to this number from this and this, but you got to know. If I want to know that, see, I don't know how you would do that because if I do that, if I take this away and I put the equal to. Now, because I said I don't know how you would do it, doesn't mean that you can't do it. I mean, that's the fun part. How would you figure out how to do this? If I know that this is n sec over n prime. So I can measure this with my digital multimeter. I can measure this with my digital multimeter. But then over here, I got a problem. I need one more of these. I need one of this. I need one to get the other. And without counting them, I don't know how you would do that. And if you ever look at a transformer, you do not want to count it. But is there a way to get it? Well, it probably is. If I can, what if I did this? I know, what if I can figure out, I can measure a piece of wire and figure out the ohms per centimeter. So is there a way to measure and get that? There should be a way to do it without actually counting it.
Yeah, you have to know the properties of what the coil's made out of.
Yeah. Well, I think it's doable. If they gave you $1,000 and some time, or maybe $10,000 and some time.
I need more than $1,000 to do that shit.
It's doable though. Okay, that's all I have, guys. Have a great rest of the day. Now remember, please, I'm gonna go up and check to see if the guy emailed me back from the lab center. If not, look for me to communicate with you today, later today or tomorrow, to see if we're going to do this on Wednesday. If he doesn't get back with me, we won't be able to do it unless we do it another day other than Wednesday. But I don't know we might have all different schedules. I don't know what your schedule is. So if we do it on the day that we're scheduled to have class, it's better for everybody, but we'll see. So just kind of watch your email in case I email you. If I don't know by late tomorrow, if he gets back with me Wednesday morning, I don't know if that's enough time for you guys. I mean, I think I got everybody's phone number. Is Randall in there? But you guys know how to get a hold of him. Is he in there? Oh, he is. Yeah, he is here. Okay. So if we have to do that and everybody's in town, I don't know if Wednesday, if they got back to me on Wednesday, if that's too late or not. So we'll see. Somebody sent a message. I missed it.
Yeah, that was just me. It's Randy. I actually have Jacob's number though, so he can text me if you plan anything.
Okay. So if we can do this, I'm hoping he gets back with me today, no later than tomorrow morning. But if not, then if Wednesday morning is an option, if that's not too late for us, you guys to change your plan and say, hey, we want to the school, we'll try to make it work. But we got to because I don't know what way he's going. Is he even teaching AC? Is there another? I don't know if there's another AC or not, but I don't know how we're gonna do it other than that. I just don't know what to do. So, guys, have a great rest of the day. If you need me, just send me a text. Go ahead and text me anyway for attendance. I haven't taken attendance in a while, so I don't know if you remember the number, but let me put it up here. Send me a text for attendance. 494-6162, and it's EET 132. And just put your name in there and you're good. And I will see you Wednesday, hopefully at the school. I want to go up to the school. I miss it. So I'll see you later.
Do you think that would start at 2 o'clock, or would it go back to the 1 o'clock one?
If we go up to the school, I want to do we'll do it from 1 o'clock to 3 o'clock. That way, in case you got
Okay.
something to do after that, you have enough time for what you want to do.
Okay.
So
okay.
we'll just
I
do a
wanted
couple
to-
hours.
Okay, I just started a job, and I'm getting off, and then you need to know before that. That's fine. Sounds
Yeah,
good.
okay, and if it interferes with something, we'll work it out. We can be flexible. I think it's few of us enough that we can work it out. So don't worry about anything like that. Okay, guys, see you later.